I would just like to, I suppose, welcome you to the best practices session, and thank you for coming. Just a bit of housekeeping before I start is that all the Q&As, you're welcome to ask questions at any point throughout the sessions, and there is a live Q&A box on the right-hand side of your screen. If you're experiencing any technical difficulties, there's also up the top of your screen some live support that you can avail of. So this session will end promptly at 11:20, so 20 minutes per speaker with questions included in that. So we want to stick to the time as much as possible. And I am the session chair. A little bit about myself is my name is Anne McCartney, and I did a postdoc with Genomics Aotearoa and with Manaki Whenua for the past 2 years, and I'm just after relocating to work in the NIH in Washington, DC, so it's actually 6 o'clock here. And I basically do all of any genome assembly work that you need. So I won't take up too much more time talking about myself. I will introduce the first speaker. So we have two great speakers lined up for this session. And our first speaker is Dr. Alexander Pletzer, and he's from NeSI, and he is based in NeSI in Wellington. And he's going to teach us how to harness the computational power of NeSI to get the most out of our workflows. So I'll hand it over to you, Alexander.
Thanks for the introduction, Anne. Let me share my slides. Whoops. Can people see that? Okay, I'll start the right. Okay. How is that? Is that looking okay? Can people see? Can people see okay? Yep.
Yes.
I see a thumbs up. Yeah, it's coming up. Okay, so so this is really about harnessing more compute power at NeSI. So NeSI is the New Zealand eScience infrastructure running on supercomputers in New Zealand. I think the organization should be well known, but maybe there are some overseas attendees who are not familiar with NeSI. And today I'm going to talk about open multiprocessing, which is usually known as OpenMP. So the just a brief little overview of what NeSI does, just services everything around research computing, whether it's support, whether it's data transfer. Obviously, we have our own hardware, and we provide training, as well as consultancy. So we're always there to help researchers run better and faster on our platform. So the workhorse of NeSI are essentially two computers. The one on the left is called Mahuika. It's a capacity machine, and we use this platform to run lots of smaller jobs, things that normally don't really scale very well, but you know, may run for a very long time on a modest number of cores. And then on the right-hand side, that's the green machine, which is called Maui. And Maui is a capability machine, so it's not meant to run a lot of jobs, but the jobs tend to be much larger, so they may use several nodes. Each node might have, you know, 40 cores or so, and you can use so you can really scale horizontally. The reason why I'm talking about OpenMP is that we're living a little bit in a crisis at this point, and not because of COVID or other things, but simply because the processors are not getting any faster, and so but research still wants to evolve and improve, and so our computing capability must keep up, you know, with the demands of advancing science, and so really one way to harness more compute power is to use more cores, and that's what I'm going to talk about today. There are different ways of leveraging more cores. I mean, one way is to just call a library that is multi-threaded. An example is the math kernel library of the Intel, from Intel, SciPy, these libraries, they're already multi-threaded. You just link against them. You use the setup, and then you can leverage the parallelism through the library, so you don't have to actually make any changes in your code. The other way is to use OpenMP as a springboard to parallel computing, and that's something that works quite well, because if you have a code that needs to run faster, you can just look at a certain section of your code, focus on that particular code, and add some directives, OpenMP directives. That's a good way. And thirdly, even if you have a parallel code and so forth, really, if you want to tickle that high-end scalability, then probably you want to run in hybrid mode, MPI and OpenMP. So I'll go through a couple of cases here, but this is just a code that we have written specifically for training. It's a scattering code, so you have a wave coming from the left-hand side, you have an object, and sort of the waves bounce back. It's written in Python, and what we found was that it was also through that particular exercise. But on the left hand side here, you have the original performance of the code. So you have a speed up of 1, and and as we modify the code, we improve the performance, and you can see that at some point, we use Numba, which is a Python library, and we got maybe 18 and so forth, and sort of things go up. But really, the best performance is that bar on the extreme right, OpenMP with 8 threads, and using some external, essentially rewriting some of the code in C. And then with that, we actually got a factor more than 100. The other use case is what is called a FIDI bench. It's a code that is written in different languages, and so we can compare the performances of various languages. It's written currently in C++, Fortran, Python, and Julia, and then we try some programming techniques on that particular code to see how it performs, and it has a computational sort of the compute pattern of many finite difference volume and element codes. What happens here is that you have that blob, that bubble here in red, and it's sort of advected. Sorry, it's advected in space. So so you have a little bit of sort of neighboring communication, and you can play with MPI, OpenMP, and other technologies. And what we found in that particular case is so we have these two platforms. Remember Mahuika and Maui. Mahuika is a capacity machine. Maui is the capability machine. And now the capability machine has the better processors. It's about 40% faster. That's quite nice. But as we add threads, then the computational time sort of drops. Good thing, and that's really what we want. But at the end, at the high end of sort of one node scalability, you get about the same performance between Maui and Mahuika. So the processor doesn't really matter that much anymore. I mean, it's all just the load balancing and other issues that become dominant. So it's no longer limited by sort of computational power, but it's more sort of communication and other things that enter into the game. Well, there's one thing that is really exciting with OpenMP. OpenMP is a standard that started at the end of the 90s, and it was meant to be really simple. And over time, every version adds a little bit more complexity, but you can do more things. And so one thing that you can do now is you can, in OpenMP, you can actually offload some computations to a GPU. We have a small number of GPUs, a P100. They used to be really nice GPUs, but now they have been superseded by GPUs that are much faster. Nevertheless, Nevertheless, what you see here in the graphic on the right-hand side is so these are the times. So the lower the better execution time, and you add some threads and things come down. That's the same curve we saw before. That's the dashed one, but now you offload the computation to a GPU, and you get the light blue line. That was using the Cray compiler last year. Then we had a consultancy yesterday. We had Damien Mather and Chris Scott talking about OpenACC for a consultancy, and they installed a PGI compiler. And the good thing, because we got even better performance with the PGI compiler for that particular case. So that's the light sort of brown line. And so what you see here is that we actually beating, by shifting, moving, offloading the computation to the GPU, we can actually do better than on a single node. Not much better, but a little bit better. Now imagine that we get the next generation of GPUs that are maybe 5, 6, 7, 9 times faster, and then suddenly it could potentially be a real winner. So the last example I just wanted to mention was the ELFRIC code, which is a next generation weather and climate code that we also involved at NeSI with. We partnering with UK Met Office. UK Met Office is really in the driving seat here, but we contributing, and they here I'm sharing some results from a study by our colleagues in Australia, and they I think they looked at the at how the time comes down, with the number of nodes. But really, I think the major point here is that when you really go down to a lot of nodes, then actually adding MPI gets you that little bit of scalability that can help you in increasing the performance. And so that's something that is important for these people. And the way it works is that you're doing MPI essentially on the plane, on the horizontal plane, and then you're doing MPI on the horizontal plane, and then OpenMP vertically. So you combine two forms of parallelism. So we learned a couple of lessons, and one of the lessons that we learned, and I'm not showing the results here, but originally we had our sort of benchmark code, and we performed really poorly with OpenMP, and we were wondering why. And then suddenly we found out that there was some heap allocation going on, which in the context of OpenMP didn't work very well. And so we moved the allocation to the stack, and then poof, the bottleneck evaporated. Obviously so the GPU is really very attractive, but in the context of OpenMP, it makes OpenMP significantly more complex. However, there's that other technology, OpenACC, which was mentioned yesterday in a session by Damien and Chris. It's very similar to OpenMP. I mean, it works, the language is a little different, but the idea is very similar. And that's another way of running faster, which is worth considering. We also observed that OpenMP, when offloading to the GPU, currently is slower than OpenACC. We're not exactly sure why, but presumably it's just because it's a sort of a new addition to OpenMP, and so they probably play safe and do things that are not necessarily the most efficient, but ensure that the code runs okay. So in summary, so we actively promoting OpenMP and OpenACC actually as well at NeSI. We think it's a great entry point for users who want to do parallel computing or want to offload to a GPU. We, of course, are very glad to see compilers adopting OpenMP5, the latest standard, but some vendors are dragging their feet. And I think the other message is that life is becoming more complex in some sense. I mean, you have the CPU, you have the GPU, you have multi-threading, you have MPI, and you have all these kinds of things. So more degrees of freedom to play with, and of course more opportunities to get, you know, that additional little something that will get you code to run faster. So the just talk to us in this conference or off conference. NeSI provides engineers, you know, to help researchers. It's typically free of cost if you are a subscriber of NeSI. And we tend to then publish case studies. So that's something. So we want to work with the research. I think it's very important for us as part of NeSI to be involved with the research so that we understand what the need of our users are. And so thank you. And time for question.
Sorry. Thanks, Alex. That was great. Now, we did have a few questions being asked, and the first one was from Jean.
Yeah.
And Jean is wondering, would you prefer OpenMP4 over OpenACC, and if not, why?
Yeah, so I think in due time, I think OpenMP will just replace OpenACC, but at present, I think OpenACC has an edge over OpenMP, and so it does make sense to use OpenACC over OpenMP. This might change, you know, over time, and so it depends. I mean, I guess it's easier to start with OpenACC, but you know, once you have OpenACC, then you might be able to convert that to OpenMP fairly easily, because it's based on sort of pragmas. So you know, there's sort of similarity between the two approaches.
Okay, thanks. I think that answered that question. We have another one just come in. It's from Joaquin. You mentioned a code that compares languages. How does Julia parallel code compare to OpenMP with other languages?
Yeah, so the Julia version of the finite difference code that I mentioned was not parallelized in any way. And so but we'd be happy to work with anybody to you know, bring that parallelization in so that we can exploit you know, that level. Essentially, most of us sort of lacking experience with Julia. I know, Joachim, that you're an expert, and so we would be happy to share the code with you, and if you wanted to add you know, the parallel constructs in it, that would be fantastic. We essentially relying on the community to and experts in that particular area to contribute. I hope I answered the question somewhat. I mean, it was I guess one thing that I could say was that we compared it mostly with the you know, Python and Julia, and Julia was faster than Python. But once you do the vectorization using NumPy in Python, then actually Python had an edge, but it was an old version of Julia. So again, that needs to be revisited.
Okay, I think that answers that, and sounds like a good opportunity to collaborate with an expert in that language. So I do have questions, but I will wait. But I would like to introduce now our second speaker, who is Dr. Chris Seal. And he carried out his PhD in the University of Auckland. He then moved and did a postdoc in the University of Manchester. And he's now back in New Zealand and working for eResearch and actually listening to user experiences and trying to better the MyDardis data repository. So I'll leave it over to you, Chris, to get started.
Thanks, Anne. Hopefully I can now just share my screen. And I hope everybody can see that now. If I share the right one. Yep, cool. So thank you for the introduction. Today I'd like to talk a little bit about my experiences with customizing an open source project, and then hopefully open the floor to a discussion to get some experience from others who have done similar. With that in mind, and given we have these shiny new tools, I'm going to start a poll there's only been one, just to ask if you have had experience contributing to an open source project in the past. Before I start, I figured I would give you a little bit of an introduction into my background. When I was growing up, I had two kind of skills. I was quite good at building things, and I was much better at breaking them. So you put those two together, and that ends up in the engineering school at the University of Auckland, where I ended up breaking pieces of steel. As Anne mentioned, I took a postdoc in Manchester, where I took my love of breaking steel and moved it into the digital space. The end of 2017, I returned, and about June last year, I ended up, I've been fortunate enough to work for the Centre for eResearch, where some of the Python in particular coding skills that I picked up in Manchester we've been putting to good use. I'm going to talk first about my TARDIS, the project that we are implementing. Then going to walk through the decision-making process that we went through and what the consequences of the choices we made were, and the steps that we've taken to mitigate those choices. So when I first started, much to my disappointment, my TARDIS didn't have anything to do with Doctor Who, but looking in it, it's actually, I think, probably more interesting. So my TARDIS is an instrument data repository. And if you think about a piece of scientific equipment, you take a measurement using that equipment, and you have two sources of data that are generated. There's the measurement itself, and there's the information about the machine and the conditions that we used to generate that measurement. So we take those two sources of data and we split them. The data, which is the measurement, we put into storage, and then the metadata, which is all that information about the experiment setup and the instrument, go into my TARDIS. My TARDIS talks to the data storage, it knows where that data is located, and it provides a web front end so that different groups of users can log in to the portal. They can see a curated view of the data, so they only see stuff that they are allowed to see. And in some cases, we provide access to the measurement itself so that that can be downloaded by researchers to do further analysis on, for example. It's an open source project that was originally developed by Monash, and its original purpose was to store data that was generated at the Australian synchrotron. Since then, it's grown somewhat, and now there are more than 100 instruments at Monash alone, and they have collected more than 1.3 petabytes worth of data now. So these results are slightly old. In a nutshell, it's a database. We have a hierarchical structure where we have experiments which contain data sets, which contain the data files that are generated from the piece of equipment you're using. We use Django as a web front end, and that connects to the database. In our case, we're using Postgres, and the storage, which we're using Ceph with an S3 front end to our Ceph storage. Communication between all the parts is mediated by a Rabbit messaging queue with Celery providing workers. And in our case, all of that is sitting on the Auckland node of the Nectar Research Cloud. So when we started with this project, the first thing we did was spin up a version of the community edition of my TARDIS and take this to potential users. We sat down with researchers and asked them what they liked about it and what they thought was missing from the project. There were lots of feature requests that came in, but there were a couple that we thought might be a little bit difficult or might be a bit troublesome. The first was that access control on Mitatis was fairly coarse-grained, and speaking with researchers, they needed better control over who could see what. The second was that the search functionality that was built into Mitatis was fairly simplistic, and it didn't currently index metadata. The reason for that is because of the structure of the metadata within Mitatis. Unlike a lot of the more discipline-specific repositories that are available, Mitatis is designed to be generic so that it's able to accommodate different instruments. And as a result, there's no standard metadata schema that can be hard-coded into the database. So it has quite an abstracted method of being able to add flexible metadata. And we have to be able to walk through that level of abstraction in order to be able to get parameter names and their values for indexing search. So we had this collection of changes that researchers wanted. We then really were faced with two choices. Either we stick with the community version and accept the limitations, or because it's an open source project, we fork that branch and accept the consequences of forking that branch in terms of additional development, and also things like maintenance, ongoing development to keep parity with upstream. So the first question we asked ourselves was actually, is it a problem? And that can be looked at in one of two ways. Firstly, is this an unreasonable request from our users? We thought no, actually they were quite reasonable requests. And the second is, how much will we need to touch the existing code base? So if we're able to add an addition without affecting upstream significantly, then we'll have relatively few merge conflicts when we try and bring ourselves up to parity with upstream. So the maintenance side of things would be relatively straightforward. When we were thinking about that, we had a suspicion that actually both search and access control were going to touch many parts of the code. Which led us to the second question, which is, we've surveyed some researchers, but we haven't widely surveyed. Are the requests that they want, the features that they want to see implemented, more specialized, or are we likely to see these being common across a range of different research groups? Particularly with search, we thought actually that's something that most people are going to want to see. Which then led us to, well, if it's going to be used by our researchers, will it also be used by other researchers? And can we feed this back into the Mitatis community as a whole? So we decided based on that, that we would fork the project and we would create a University of Auckland specific branch of the Mitatis project. We then had to start thinking about how we manage our code base. So in terms of consequences, having made that decision, as expected, when we started looking at access control lists, we ended up touching over 250,000+ files that made up the project. So we have code changes all through Mitatis. And that means that when we go to merge with upstream, there are a number of conflicts, and there's quite a bit of development time involved in identifying those conflicts and resolving them. We also were under some time pressure and adopted the motto of don't let perfect be the enemy of good. As a consequence of that, many of the tests that were built into the original project we broke and we haven't yet got around to fixing, which, as I'm sure most of you are aware, is a bad idea. But given the constraints we were working to, we would probably do it again if we had to start over. So the first mitigation strategy that we're applying is implementing a more robust DevOps approach. Now that we have some time, now we've got a stable release, we're fixing all of the tests that we broke, and we're looking to implement a automated deployment. We're looking carefully at upstream changes, and we are not automatically adopting upstream changes. We're looking to see whether or not there are significant reasons to adopt an upstream change. And that means that we are missing on some of the minor releases of the community edition of Mitatis. But our number one mitigation strategy was actually to embrace the open source methodology. We've been actively engaged with the Mitatis community. We have a monthly meeting where we meet with other Mitatis users and the main branch upstream maintainers. And as expected, some of the changes that we thought would be more widely implemented have been adopted and are in the process of being adopted by the community edition of Mitatis. So we've submitted pull requests where we're contributing our code back to that main branch. That's got a number of advantages. For us, if the main branch adopts a lot of our code changes, then it makes our merge conflicts much fewer and easier to deal with when we do decide that we need to migrate to a more recent version of the community edition. That in turn means that when we take it into our sandbox for testing, there are fewer things that have broken, and there are fewer things that we need to test rigorously, which means that we get new releases out a lot quicker. So looking kind of to the future, I think the takeaway that I have taken from this is that there is a real advantage in working collaboratively. So we've worked collaboratively with researchers and facility managers to identify what their requirements are. As a result of that, I think we have identified features that we're missing that we feel benefit Mitatis as a whole. We've collaborated with the Mitatis community, and as a result of that, we've been able to feed those changes back, which again is a win-win situation. It means there's less maintenance for us if we continue to maintain parity with the upstream code base, but also we're providing features and functionality that have been wanted by the Mitatis user community for some time now. And we are now in the process of extending that collaboration to other communities of interest. In particular, we're working with Research Data Alliance to integrate persistent identifiers. And this is something that we believe will help our researchers by being able to cite an identifier similar to a DOI, which contains information about the equipment they've used and information about the testing that's been done. So I guess the story that I want to extend to you and is our experience where we've gone from converging, from moving our code base away from the community edition, and through collaboration and engagement, we've now started to bring that back. In conclusion, I'd like to ask those of you who have been involved in working in an open source project before, how have you managed that tension between wanting to add features but not wanting to necessarily take on a significant maintenance burden when you maintain parity with upstream? on that note, I'd like to thank you all, and I'll take any questions.
Awesome. Thank you so much, Chris. That was really, really interesting. We did get a question in from James Cooper, who asked, did you think it would be possible to convert all, most or all of your current changes from upstream into automatic patching so that you could use most of the process of moving to a new upstream release?
It's something that we're currently looking at, and I think it will help, but it's not going to eliminate the issues that we run into. Part of the problem that we have caused ourselves is we've added access control lists to objects that didn't have access control lists attached to them. And that has sort of effects that flow out throughout the whole of the project. So we can implement our code changes through an automatic patching system. But there have been, in my experience with this, unintended consequences of making those changes. And we've had to make code changes to parts of the project that when we started, I wouldn't have thought we would need to.
Great. We have another question from Hilary. So it sounds like not all of your new features have been accepted by the community edition maintainers. Did you find out ahead of time if that would be the case? If so, maybe their reasons would have weighed against making those changes, in which case we could have just worked to improve the community edition.
Yeah, I mean, you're right, we haven't had all of our features implemented. And again, we went through similar kind of decision-making processes. One example that sort of stands out is that we've added an additional level of hierarchy to our data structure. So we have a project level that sits on top of the experiment level. On the balance, we thought that while that wasn't something that necessarily was going to be picked up by the community as a whole, it tied into other university systems that we had, and it was a better fit for the sort of university approach to maintaining or managing research. So looking at the balance of it, we decided that it would be better for us to make those changes than not. And we went through a similar kind of change decision-making process with all of those changes.
Yeah, I suppose just on listening to your talk, I was thinking, God, if you guys are implementing a lot of changes and then they're not adopted by the community, essentially you are like removing yourself further and further away from the community, which is kind of frightening. In case the further you move away.
Yeah, and that was one of the big. I mean, it really the two items that I highlighted were the two big ones. They were the two changes that affected the biggest portion of the code base. Other changes were relatively minor. So adopting upstream changes, if we didn't have the ACL changes and we didn't have the search changes, would be a fairly simple git merge. There'd be a few conflicts that we needed to deal with, but it wouldn't be a big overhead. But because we touched so much of the code base and because there were so many unexpected interactions with those two particular changes we made, we're really quite relieved that they have decided that they want to adopt them.
Okay, I don't mean to cut you off, but we are going to be cut off. Back to the name.
Thank you.